This lecture reinforces material found in section 2.1, Earth spins on its axis. This is a hands-on activity that explains how to find the local time by looking at the stars. As we've seen, the daily apparent motion of stars is counterclockwise around Polaris when looking due north, and when looking due south, the stars rise in the east, rotate clockwise, and set in the west. This is, of course, a northern hemisphere observer. The daily apparent motion of the stars and sun can be used to estimate the local time. The learning goal of this lecture is to find out how the local time can be determined from looking at the Big Dipper, the Little Dipper, and Cassiopeia at night. Most people can find the Big Dipper, an asterism in the constellation Ursa Major, in the night sky, since it looks like the ladle with a handle and a cup. Today we will see the stars Dubhe and Merak at the front of the ladle's cup. We will see that the line formed from these two stars and Polaris, the North Star, is like an hour hand of a clock and useful for determining time. The University of Nebraska's Big Dipper clock simulation shows how the stars rotate daily and gives their orientation for a given day of the year and local time. This is the position of the Big Dipper, Little Dipper, and Cassiopeia at local midnight on the autumnal equinox. At midnight on the autumnal equinox, the hour hand of the Big Dipper clock is vertical to the local horizon. The hour hand of that 24-hour clock is vertical as well. Notice the clock in the Dipper clock simulation is a 24-hour clock and not the standard 12-hour clock that we typically see on the walls of offices. Let's look at how the Big Dipper clock arm moves over the course of a day. As the hour arm moves clockwise 1 hour on the 24-hour clock, the Dipper clock arm moves roughly 15 degrees counterclockwise. Watch. At local time of 7 a.m., scattered light from the rising sun makes the stars difficult to see. During the day, although we do not see them with our eyes, the stars are continuing their apparent rotational motion around Polaris. At local time of 7 p.m., the sun begins to set, and we can start to see the brightest stars. Here's where the stars are, but they will move by the time they have become easily spotted in the night sky. On September 22nd, at local midnight, the clock arm is almost at the same position as it was on September 21st at local midnight. Going back and forth, we see very slight change in the orientation daily. On September 22nd at local midnight, the clock arm is almost in the same position as it was on the September 21st at local midnight. Going back and forth, we see the very slight change in orientation daily. This very slight change is due to the Earth orbiting the Sun. Every day, the midnight shifts roughly 1 degree in the sky, and that is because there are 365 days in a year and 360 degrees in a circle. It's just slightly less than 1 degree. The University of Nebraska's Big Dipper clock simulation shows how the stars rotate daily and how these orientations shift from day to day. Again, this is the position of the Big Dipper, Little Dipper, and Cassiopeia at local midnight on the autumnal equinox. Let's consider the annual variation. Let's look at the position of the stars at local midnight throughout the year. This is the position of the Big Dipper, Little Dipper, and Cassiopeia at local midnight on the winter solstice. It is the same position they were around sunrise on September 21st. This is the position of the Big Dipper, Little Dipper, and Cassiopeia at local midnight on the vernal equinox. It is the same position they were on around noon on September 21st. This is the orientation of the dippers at local midnight on the summer solstice. It is the same position as around local sunset on September 21st. For the observation journal labs to determine time from stars, a clock is constructed and used to find local time after sunset. This is the star clock template. It can be downloaded from the resources folder on Blackboard, printed out on cardstock or on regular paper that is then glued to a folder. You also need a brass brad fastener. Since the online clock template had so much black ink, which can be expensive and messy to print, I've made an alternative template for you. Both are included in the resource folder. You can choose which one you prefer to use. If you like to write programs or are studying computer science, the MATLAB code for reproducing these star clock figures is in the comment section of the star clock template PowerPoint. Cut out the outer circle of the month and time and the inner circle of the constellation patterns. Insert the brass spring fastener to assemble such that the wheel can turn independently. Look at the north after sunset. Find the Big Dipper asterism in the constellation Ursa Major. Find Polaris from the pointer stars of the Big Dipper asterism in the constellation Ursa Major. Turn the outer circle of the star clock so that the current month is at the top. Turn the inner circle until the picture of the Big Dipper matches the Big Dipper orientation in the sky. Read this time in the window. Add an hour if it is daylight savings time. Compare star clock time to the actual time given by a reliable timekeeping device. The star clock is not that accurate. It is difficult to orient the day of the month to the top and find the star pattern match. For your lab, you should complete the activity and then make a journal entry. Your report should include the following. Observation location, always include some sort of street address, unambiguous landmark, or latitude, longitude. Observation date and local time. Weather conditions, such as cloud coverage and precipitation. Observation description, describe what the sky looked like at the time. And answer the following questions. What time was on the star clock, and how close was the star clock to the actual time? In the southern hemisphere, Polaris is not visible. This Pearson Interactive shows how the Southern Cross can be used as a star clock there. The link is available on Blackboard. Vincent van Gogh's Starry Night over the Rhone was painted September 1888 in France. Use the star clock to estimate the time. Check your answer in the resource folder or pause the video and the answer will be given in a second. The solution is the painting was reproducing the star pattern of about 10:30 p.m. local time on September 25th, 1888. There's more interesting things about how this painting was put together at the website above.